right, guys. This is me upstairs in my house. I just wanted to work a problem for you, similar to what I put on the WebAssign, where you're finding essentially local maxes and local mins for a function that's maybe a little bit more complicated than maybe even some of the ones that I gave you. These problems take a while to actually do. And so I didn't want to take an entire class time because I'd feel rushed to do it. Where here, if I just make a video, you can scroll through as quickly as you want. But I just want to work through something where I don't feel rushed and I give you enough details so that maybe you can apply what I show to your problems. These problems take a while. Think of them as like eating a French meal. It's nothing you want to rush. I don't know where that dumb analogy came from. Sorry. Okay, I need students to teach. So we've got a surface f of xy is equal to y squared minus 2y cosine of x. So once again, f of xy is equal to y squared. I'm just going to make sure you can actually see what I wrote there, and I think you can. Y squared minus 2y times the cosine of x, and they're limiting the rectangle of interest where x is going between minus 1 and 7, and y is running between minus infinity to infinity. And what we're trying to do is to find all the local maxes and local mins for this function. Okay, so the first thing that we want to do is we want to find all the critical points. Now we remember that from Math 235 that the critical points are where the derivative is equal to 0. And the natural extension of the derivative being equal to 0 to higher dimensions was what? Do you remember? And hopefully somebody's saying, yes, Dr. Warren, I remember. It's the gradient, okay? So we're looking at for all the possible values, A, B. Let's see, maybe I can get a better, fresher marker here. A, B, such that the gradient of the surface evaluated AB is equal to 0. So it's the natural extension, or the gradient doesn't exist, But for the problems that we're going to be dealing with, we're not going to be concerned with that. Okay, so we're looking for all the places where the gradient would be 0. Okay, now remember what the gradient is. The gradient vector at a point AB is the vector that's the partial derivative with respect to x evaluated at AB is the first component, and the partial derivative of f with respect to y of AB is in fact the second component. So now what I want you guys to do is pause me right now, and then I want you to take the partial derivatives. I want you to take the partial derivatives with respect to x and take the partial derivatives with respect to y. And I'm going to grab myself even another marker. So you pause me and you take those partial derivatives. Okay, so now hopefully you've unpaused me, and now you're going to watch me do it, and you're going to see how you did. Okay, so if I'm taking the partial derivative of f with respect to x, well, that looks better. Then I'm treating y as a constant. So if I'm thinking of like this y squared, it's like the number 7. And the derivative of 7 would be 0. I think about this as being minus 2y. But this is just like another constant. So I finally run into a function of x over here. So if I'm thinking about taking the partial derivative of f with respect to y, partial derivative of f with respect to x, this would be 0. We'd have the minus 2y, which is like a constant as far as x is concerned. And then the derivative of this would be a minus sine of x And then this minus is going to interact with that minus, and we'd get 2y times the sine of x. And hopefully that's what you got. Now let's look at the partial derivative of f with respect to y. The other component in our multidimensional derivative, okay? And so if I do that, now I'm thinking as x as a constant. So this cosine of x we can think of as like the number 5. It's not going to interact with my partial derivative. Now here I've got a function of y, so I have 2y minus 2 times that constant times y, which would just be minus 2 times that constant. Now, is that what you got? If not, you want to go back and check and see maybe where you might have made a mistake. Now, we're looking for values, a and b, all possible values that would make this gradient equal to 0. So we need both of these components to be 0, and that's what's crucial. Okay, so I'm going to start with this guy. Okay, so if I look here, I'm looking for all possible points down here in the xy plane that would make this equal to 0. And so if I look at this and I just set this equal to 0, what I see is I've got a product of 2 real values that is equal to 0, and the only way that that's going to take place with the algebra of our real number system is if either this is 0 or that's 0. So one thing, 2's never going to be 0. So one thing that we see is that y could be 0. As long as y is 0, we're running on the x-axis, that would be enough to make all those points make this guy 0. But also we could have the possibility that sine could be 0. So another possibility is that sine of x could be 0. Now sine's 0 a lot, okay? But this is where this restriction comes in our domain. We know that x is running between -1 and 7. Okay, so if we go back and think about the unit circle here, so we've got our unit circle. This is 0, this is 2 pi. 2 pi is roughly 6, okay? Pi over 2 is more than 1. So we see that all possible values that are going to make sine 0 are going to occur in this first revolution here. So let's think about it. When will sine be 0? Well, it would be 0 certainly when we're at 0. It's the y component of the point on the unit circle. So we'd have 0. We'd also be 0 over here at pi. That would be in that part of my domain. And then if I come back over here, also at 2 pi, which is less than 7, 6-ish. So I have 3 possible values here. Sine would be 0. This would imply that x could be equal to 0, pi, or 2 pi. X could be equal to 0, pi, or 2 pi. So these are the possibilities for making this first component of my gradient equal to 0. So anybody on here, and then the possibilities that x could be 0, pi, or 2 pi. Now hopefully that's making sense. The other thing is I need this other component to be 0, and that's where the critical points are going to start becoming more concrete. So we not only need this guy to be 0, which we've just taken care of. These are all the possibilities that I've got. But we also need this other component to be 0. Okay? So now let's start examining this second condition. with each one of these constraints that we found from our first, looking at our first component there. So I'm gonna look here and I'm gonna say, okay, well, let's look at y equals 0. If we look at y equals 0, if we take this first condition, okay, we know this guy's 0, that top one's 0. But if I make y equals 0 and I just plug it in here, okay, then I would know if I had this, then that fy, I'm not going to do this for every single one, of x of 0, well, then I would have that this would be equal to minus 2 cosine of x. Now, when will cosine be 0? Well, again, we're back on the unit circle, and if we're back on the unit circle, we know that cosine's 1 here, but when I hit like those 90 degree, those 90 degree points where we're looking here and then down here, you know, our pi over 2 and our 3 pi over 2, that would be places that would make this 0. So if we want this to be 0 under this condition, then we would also, this would imply that for x in that range, that x could be pi over 2, that would make this 0. And also down here, which is 3 pi over 2. And so we found our first 2 critical points. Nice and slow. We found our first 2 critical points. So if I put my critical points here, if I start listing them out, I see that if x is pi over 2, if x is pi over 2 and y is 0, because that was the condition that we started with here, then it would make both components 0, making a flat tangent plane. And we also have that 3 pi over 2 and 0 would also make my gradient equal to 0, giving me a flat tangent plane, giving the possibility that I could have a local max or local min. And you're like, oh, Dr. Warren, are you done? And the answer is no. We still have a lot more values over here to still check. So now what I want you guys to do is I want you guys to take this guy, take x equals 0, use that as a condition, look at the partial derivative with respect to y, set it equal to 0 and see if you can come up with a possible other critical points for just x equals 0. So you go ahead and you do that. Now you can unpause me and I'm going to do the same thing. So if I'm looking at x equals 0, which was another possibility, okay, and I would plug that into my partial derivative, meaning now I'm just going to have a function of y. So I plug x equals 0 in, and you guys are going to help me out. When I plug in x equals 0 in, I'm going to get cosine of 0, which you better know is 1. Okay, and so this would give me the function 2y minus 2. Now again, we're looking for places where this would be 0, so we set this equal to 0. And I'm hoping this is not difficult for you to find. There's only one value that's going to make this 0, and that would imply that y's got to be equal to 1. So when x is 0 and y is 1, again, this will be 0 and that will be 0, which again would be another critical point. So we'll add this to our list of critical points over here, and you guys make sure I don't make a mistake. 0, 1. Okay, now that we've done that, I want you guys to try x equals pi. We know it makes the first one, we know it makes this first component, my partial derivative with respect to x, 0. Now you try to find, are there going to be any y values that would also make the second component 0? So pause. Push the pause button. You better be pausing. You better not be playing games. I'm teaching you. Okay. unpause me. Hopefully you unpause me. Now I'm going to do the same thing. So I've got the partial derivative of f with respect to y. I'm evaluating that at pi, which is then going to leave me only a function of y. Okay, so now where I see the x, I'm going to put the pi. Almost dropped my 2. Cosine of pi. Okay, you know what, Dr. Warren, I'll never figure out the cosine of pi. You can figure out the cosine of pi. You come up here, you look on the unit circle, you're all the way over there. What's the x coordinate? Well, it ain't 0. What is it? Oh, did you say -1? That's right, it is -1. And so using that, if this is -1, then this is 2y plus 2. And the only value of y that's going to make that 0, is y equals -1. And yet there's another critical point. We know that when x is pi and y is -1, that we have another critical point. And that's going to be the only values that will work for that. And again, that will make my gradient 0, nice flat tangent plane, possibility for a local max or local min. Now we're almost done. We've got to get our 2 pi. X equals 2 pi. Now I know I'm right in front of you. Here's x equals 2 pi. I plug it in to there. And when I do that, I'm all the way back at 0. But we know already that that's 1. We actually did that case right here. And so just doing the same kind of analysis, we can see that we'll end up with the same thing because if I put 2 pi in there, I'm going to get a 1. I get the 2y minus 2, so y equals 1. So my other critical point, I know I'm going fast. You can figure it out. My other critical point, my final critical point, is going to be 2 pi 1. And those are my 5 critical points. You're like, Dr. Warren, we must certainly be done now. No, they didn't ask us to find critical points. They want us to find the local maxes and local mins. And you're like, well, how do I do that, Dr. Warren? Well, you got to remember that discriminant with that quadratic formula that we were dealing with. You're like, Dr. Warren, I don't remember that. Well, remember the discriminant ended up leading to the following. Now I'm going to erase a good part of this because I don't have much space left here on my board. So I'll get rid of this. I'm going to get rid of all of this work for our critical points. I'm going to leave my partial derivatives here. Remember when we were analyzing, trying to determine what would make a local max or local min? What we decided was, as long as in every direction we went, along every curve, if the surface was concave up in that slice, that would imply that we had a local. A local minimum. And if it was concave down, then that would imply it had a local maximum. Okay, and that ended up running down and analyzing a quadratic formula, okay, where we were looking at the discriminant, and that discriminant ended up being and I guess I'll put in my A and my B, that if the second partial derivative, and you can go back and look at your notes where we derived this, if the second partial derivative, the mixed derivative, fxy squared minus fxx at AB and this was essentially the b squared minus 4ac. We had a 2 with this guy, so we just removed our 4. As long as this was negative, then that would mean then that that all of the parabolas we were looking at were going to be one sign. I mean, they were always going to be either going down or going up, which was going to lead to our conclusion that we had a local max or local min. Now the book does this just the opposite. They call this D, but they flip it around and put these guys first and that guy second. But with it being the discriminant the way we derived it, I much prefer this. I much prefer this because it essentially is our b squared minus 4ac. So if this is negative, okay, we know that we have a local max or a local min. When this is positive, then that means there's some directions where we're going up, we're concave up. There are other directions where we're coming off concave down, which means we have a saddle point, that we neither have a local max or a local min. And so it's all dependent upon that result right there. So we've got to analyze our critical points with this condition, and then we move further from there. So to do that, what we notice is that we need all three of these second partial derivatives. So let's start by looking at f(x)(x), which means I'm going to take the derivative of this with respect to x. Now again, y is behaving like a constant. So if I'm here and y is behaving like a constant, well, I'm going to take the derivative of sine, which we all know is cosine. So I've got this guy taken care of. Now we look at fyy of xy. Okay, so here's fy. Now we take fy, well, we notice this guy's just a constant as far as y is concerned, so that guy's going to become 0, and then we're just really left with this, that's equal to 2, which is nice. That makes this much easier to analyze. Now let's look at fxy. Let's look at fxy, okay? And so if I do that, I'm taking my partial derivative of this guy with respect to y. And if I do that, this is now a constant as far as y is concerned. And so I end up with 2 sine of x. And we can check to make sure that we did it right, because if I would take the partial derivative of this with respect to x, then as long as we have continuity, they better be the same, and these are definitely continuous functions. I see that would be 0. The derivative of cosine is minus sine, and I get the exact same thing. Are we done? No, we're not done. We've got to analyze our critical points over here. We've got to analyze our critical points over here with this condition. Now guys, this is what I typically do at this point. I make myself a nice grid because being ADD, I tend to mess things up. Now I am not going to work out all of these for you, but let me just lay out this grid the way that I would do this. Now, I don't really need these guys anymore. We're done with this. I need my partial derivatives. Let's see, clean it up real well. Try another eraser here. Yeah, still not cleaning up great. I need this. I need my critical points. And I need this condition over here. So now again, I'm not rushing. So I'm just gonna rewrite my information down here, and you can just fast forward if you want. Will I mess this up? fxx is equal to 2y cosine x. fyy equals 2. fxy equals 2 sine x. So that gives me space here to clean this up. Now, Now this is what I typically do. I make myself a nice grid. I give myself my critical points. The next thing I do is I make a column for the second derivative with respect to x. I make a column for the second derivative with respect to y. I need a little bit more space there. I make a column for the mixed partial, and then I make a column for this result here, fxyab squared minus fxxab fyyab, and you can see I've already got crap in my column here, but it's okay. Now I list my critical points here, pi over 2, 0, 3 pi over 2, 0, 2 pi 1, oh, let's keep the same order that we were going, 0, 1, and then pi negative 1, and 2 pi 1. Okay, now I can erase these. Okay, so now let's plug pi over 2, 0 into here. So if I do that, I would have that fxx at pi over 2, 0 is equal to 0 times cosine of pi over 2, which is just 0, Similarly, fxx at 3 pi over 2, 0 is going to be 0 times cosine of 3 pi over 2, which is just 0. Fxx of 0, 1. Okay, now x is 0, y is 1, so that'd be 2 times 1 times cosine of 0. But cosine of 0 back on your unit circle is just 1. So now I get 2. Now I know this is like watching paint dry, maybe even worse than watching paint dry. Maybe this is the most boring thing you've done in a long time. But I told you, I'm not going to rush this. You can fast forward. Fxx of pi negative 1 is equal to 2 times negative 1 times the cosine of pi. But the cosine of pi is negative 1, so I get these negative 1 times that negative 1, and I get a 2. Put in 2 pi. Dr. Warren, this takes forever. No, I know. It's multidimensional calculus. What'd you think? This is 2 times y, which is 1. Cosine of 2 pi, which is also 1, and I get 2. So I found that for this column, I've got 0, 0, 2, 2, 2. The nice thing is the second partial derivative with respect to y is always 2. So this one's super easy to fill in. Now we look at this guy. Okay, so we've got pi over 2, 0, but we can see that this doesn't depend at all on y. So I'm only really concerned with what I have for x. So if I plug pi over 2 in, I'm going to have 2 sine of pi over 2, which is 0. I better just check myself here. 2 of sine of pi over 2, but in the unit circle it's not 0. In the unit circle we're up here at pi over 2, which is 1. So we just get that this is 2. 3 pi over 2, 0. Well, again, if I look here, 3 pi over 2, 0. So we've got sine of 3 pi over 2. Which is 2 times negative 1. So we get minus 2. And then 0, 1, 0, 1. So if x is 0 is y is 1. So here I've got 2 sine of 0, which is just 0, and then we've got pi, negative 1, so 2 sine of pi, which is also 0, if I'm thinking about the unit circle, and then 2 sine of 2 pi, which is also 0. So again, it's not exciting, but if you just take your time, it's not like it's impossible, even for this more complicated problem. Okay, so now let's go up and look at our discriminant. So now it's pretty easy here. If we do this, we've got our 2 squared, that's this column, minus fxx, which is 0, times 2, which is 4. Okay, so the moment we look here, okay, if we were only going to have a max or min, we're only going to have a max or min when the discriminant's negative. Okay, and we can see here this certainly ain't negative, so we know that this is not going to be a local max or min. There's going to be places, because it's positive, where you're above the x-axis and where you're below the x-axis as far as that parabola is concerned, which extends to the idea that there's paths in our three-dimensional space where sometimes you're concave up, and other paths where you're concave down, and so that we're not going to have a local max or local min, but we're going to have a saddle point. So we know that at this point in time, we've analyzed that pi over 2, 0. It's a critical point, but it's not a local max or min, it's a saddle point. So now we come over here, we look at this, we square this, negative 2 squared, minus again 0 times 2, and again we get 4. Since this is positive, again the discriminant would be positive, and so we're going to have a saddle point. Okay, so now let's look at what we have here. So we have 0 squared minus 2 times 2, which is negative 4. I think we can get rid of these guys now. We don't need, oh no, we do need those guys, but it will be okay. Okay, and then we look at 0 squared minus 2 times 2. And this just works out to be pretty much the same thing. 0 squared minus 2 times 2, which is negative 4, Okay, so the discriminant is negative in each one of these cases. So we know that each one of these guys is in fact going to be a local max or min. We're going to have a local max or min at 0, 1, pi negative 1, and 2 pi 1. Now the question is it a local max or a local min? Well, remember our A, the A in that parabola was related to fxx. If we could go the other way, they'll always be the same sign. If this is in fact negative, your fyy will always have the same sign as your fxx. And if you want to remember why, go back and look at your notes from when we derived this information. So I look here, in each of these cases, these guys are always positive. This is positive, that's positive, this is positive, that's positive, this positive, and that's positive. Which means then that on every single path that I would go away from these points, I'm always going to be concave up. I'm always going to be looking up like this, which means then I'm going to have a local what? I mean, if it's always going up, it's always smiling no matter which direction I head away from my points, then I know that I'm going to have a local min. So each one of these are going to be local mins. I'm going to have a local min at 0, 1. Again, it's because this was negative, the discriminant was negative, but the thing that was in the A location, as far as our analysis with that parabola, was positive. And so I'm hoping that this, by just going through this like painfully slow. So again, what's the final information? That we have local mins. We have 3 local mins, 0, 1, pi negative 1, and 2 pi 1. Now again, I'm sorry. I know it wasn't real well rehearsed and it wasn't like amazing board work, but I'm hoping this helps because I know it would take about a half an hour to work through a problem like this, and I didn't want to rush it. And I hope this helps you with your WebAssign. Thanks for putting up with me, as always.